Welcome on. In our previous session, we have discussed about complementary function and particular integral of linear ordinary differential equations of higher order. So, in this session, we shall continue with how to determine complementary function of linear ordinary differential equation. That is nothing but how to find solution of homogeneous linear ODE. Okay, so if we see the first order linear differential equation with constant coefficient, that will be dy by dx plus a into y is equal to 0. For this differential equation, we can observe that e power minus ax, that is y is equal to e power minus ax, will be the solution. With this part, we'll go with the assumption, that is, for in general, for a differential equation, that is f of d into y is equal to 0, homogeneous part we are considering. For this differential equation, suppose y is equal to e power mx is a solution. Then if you observe here, if I consider dy, this becomes m into e power mx. D square y will be m square into e power mx. D power n into y will be m into e power mx. So m power n into e power mx. When I substitute the y in this differential equation as e power mx, this will reduce us to the form f of this d. Every time d will be replaced by m. Whenever d I had, this become m. D power d square when I had, it becomes m square. So d power n, I will get m power n. So every d term will be replaced by m into y is nothing but e power mx is equal to 0. Now if we observe this equation, here we have an exponential function which cannot be 0. Only possibility is f of m is equal to 0. We call this equation f of m is equal to 0 as auxiliary equation of given differential equation. Now, if you remember in the previous session, we had f of d is equal to a naught d power n plus a1 d power n minus 1 plus so on plus a n minus 1 into d plus n. Okay. Now f of m will be a naught m power n plus a1 m power n minus 1 plus so on plus last term will be an is equal to 0. Now this is a polynomial in terms of m. Here ai's will be constant, which we will know by knowing the differential equation. N is a order of the differential equation. So only m is an unknown. So this equation becomes a polynomial in m. By solving this polynomial, we'll get n roots of this differential equation. That is m1, m2, m3, so on up to mn. Now we have to write the complementary function yc for differential equation f of d into y is equal to 0. Or if we have only homogeneous differential equation, this is the differential equation. This complementary function is nothing but the general solution. We know the complementary function will be of the form c1y1 plus c2y2 plus so on plus cn yn. And one more condition we had here, y1, y2, so on up to yn. All these are constant, all these are linearly independent functions of x. Now, because of this linearly independent case, we have to divide the solution into different cases, namely 4 cases we have. One is when they are real, and second case is real repeated, third case is complex, and fourth case is complex repeated. Now, now if I consider the first case, the real roots, that is, let us say I have only two roots m1 and m2. If these roots are real such that m1 not equal to m2, we can write the complementary function yc is equal to c1 e power m1x plus c2 e power m2x. This is the complementary function when we have real and not equal, that is real and distinct root. The second case, if I have real but they are equal. Now the problem arises is y1 will be e power m1x, y2 will be e power m2x, but m1 and m2 are same, so m1x again. Because these two functions are one and the same, these two cannot be linearly independent. We can make that linearly independent by just considering the multiplying x here. So in that case, we'll write the complementary function yc as c1 plus c2x into e power m1x. So when we have a repeated root, I'll get c2x. Instead of only 2, if I have 3 roots are repeated, that is m1 is equal to m2 is equal to m3, we will get the complementary function will be c1 plus c2x plus c3x square into e power m1x. So there is a similarity. Even if I have 4 repeated roots, a root is repeated 4 times, we can continue with the same procedure. Now the third case comes is, suppose one root is alpha plus I beta. We know that for a real, for a polynomial with real coefficient, roots will occur, complex root will occur in conjugates. That is, if alpha plus I beta is a root, then we have another root we can directly write as alpha minus I beta. That is, alpha plus or minus I beta are roots for auxiliary equation. In this case, again, we will have here m1 y1 is equal to e power alpha plus I beta and y2 is equal to e power alpha minus I beta. Both are multiplied by x here, power x. And this can be written as e power alpha into e power I beta. Both are multiplied by x. Now, if somewhere earlier if you have seen e power I theta is cos theta plus I sin theta. Using this expansion, we can simplify the form of writing this complementary function. After simplification, we'll get this complementary function can be written as e power alpha x, this is the alpha x term, into c1 cos beta x plus c2 sin beta x. Here plus or minus does not matter, we'll always take positive sign, and because of this arbitrary constant term, that negative sign will be compensated. Okay, so this is the case when we have complex conjugate roots. The second case, the fourth and the last case is if this alpha plus I beta is a repeated root. This can occur in second degree differential equation, but this can happen only in the fourth degree. That is, alpha plus I beta is 2 times root, alpha minus I beta is 2 times root. That means there are four root. At least four root means fourth. At least we should have fourth degree, sorry, fourth order differential equation. In this case, we can write the complementary function yc is equal to e power alpha x into c1 plus c2 x into cos beta x plus c3 plus c4 x into sin beta x. This is another case of determining complementary function. Okay. These four cases are sufficient to determine complementary function for any linear ordinary differential equation with constant coefficient.